Welcome back to Catalyst Grid. My name is Kingsley Emofua, lead scheduler with DC Nordics. Today, we focus on where engineering innovation meets sustainability, the FULCRUM cooling strategy. This is the thermal heartbeat of the Hyperscale campus. This is Series 2, Episode 10, Campus Cooling, Adiabatic, Free Air and Waste Heat Recovery. We are moving from the complexities of power delivery to the precision of thermal management at the 85 megawatt scale. In Series 1, Iron Gate achieved a world-class PUE of 1.3 using water-cooled chillers, but at FULCRUM, our target is a mission-critical 1.2. To drop that final point at this massive scale, the strategy must be fundamentally different. We are aiming for zero mechanical chiller energy for more than half of the year. And most importantly, we are redirecting 85 megawatts of waste heat to thousands of local homes. This is hyperscale cooling reimagined for a net zero future. Let's look at the primary cooling mode, airside economisation. This system takes raw outdoor air, filters it, and supplies it directly to the data hall floor without ever engaging a traditional refrigeration cycle. The process is elegant in its simplicity. Outdoor air passes through high-efficiency filtration banks and an optional adiabatic pre-cooling stage before being distributed via high-velocity underfloor plenums. FULCRUM's air handling units are positioned exclusively on the north face of each hall. Hot return air is discharged well above the intake level, creating a physical barrier to prevent thermal recirculation and efficiency loss. When outdoor temperatures are below 18 degrees Celsius, we operate in full economizer mode. The mechanical chillers are completely powered down, and our instantaneous PUE approaches a remarkable 1.1. Between 18 and 28 degrees, we move into partial economizer mode. Adiabatic pre-cooling brings the supply air within range, while mechanical chillers are only partially loaded to bridge the thermal gap. On the warmest days, exceeding 28 degrees, the economizer dampers close completely. The system enters full mechanical chiller mode. In these peak conditions, the PUE rises to approximately 1.25 to maintain hall stability. In the UK climate, we benefit from over 6,200 hours of free cooling per year. Mechanical chillers are on duty for only 560 hours. This is the engineering data that underpins our weighted average PUE target. Adiabatic cooling uses water evaporation to reduce air temperature, the same physical principle as human sweating. No compressors are needed, no refrigeration, just the raw power of phase change. A high-pressure misting system reduces the intake temperature on warm days. This simple but effective addition extends our free cooling window by approximately 1,400 hours every single year. Efficiency does come with a water requirement. We consume approximately 3.5 liters per kilowatt hour of cooling delivered, with every single liter metered and reported for our monthly sustainability auditing. Safety and maintenance are critical. We use reverse osmosis to prevent hard water scaling on the nozzles, while drift eliminators and monthly quality testing ensure total compliance with strict Legionella safety standards. Finally, the system is isolated and drained when outdoor temperatures drop below 3 degrees. Antifreeze on the drain pipework ensures the infrastructure is protected from frost damage during the cold winter months. 85 megawatts of critical IT load generates exactly 85 megawatts of heat energy. At Iron Gate, that heat was simply lost to the atmosphere. At FULCRUM, we treat it as a commercial resource. We have a legally contracted waste heat export agreement. We capture hot return air from the hall and transfer that energy to the local district heating authority for use in the community. Using air-to-water heat exchangers, we capture return air at 42 degrees. High-efficiency heat pumps then lift that temperature to 58 degrees to meet the district heating network's supply requirements for domestic use. At full campus load, we can export up to 60 megawatts of thermal energy. This is enough to provide heating for approximately 12,000 homes, significantly reducing the local community's reliance on individual gas boilers. This displaced gas consumption translates directly into carbon credits. This contributes materially to our net zero obligations and provides an additional bankable revenue stream for the DBFO project. Let's break down exactly how we hit that 1.2 target. With an IT baseline of 1.0, our cooling overhead is just 0.08 thanks to the airside economizer. This is the dominant factor in our efficiency. Power conversion from UPS and transformers adds 0.07, while lighting and ancillary building systems account for the final 0.02. This brings our instantaneous auxiliary total to just 0.17. While instantaneous PUE fluctuates between 1.1 in winter and 1.25 in peak summer, our annual weighted average is 1.19, comfortably meeting the 1.2 target specified in the Cloud Core lease agreement. It's time for the series signal. Waste heat recovery is not just a sustainability afterthought. It is a material, contracted revenue stream that must be priced into your financial model from stage 2 design. For a hyperscale campus, waste heat is a commercial asset. Design it in from the very beginning of the project, not as an add-on at the end. That is how you build a bankable, truly green facility at scale. In episode 11, we look at the logistics of MEP at campus scale. We'll examine the BIM coordination and off-site fabrication program required to manage 24 different trades across 4 halls simultaneously. Thank you for joining me for this thermal deep dive. Delivering hyperscale performance while meeting net zero targets requires absolute precision and technical vision. I am Kingsley Imafua. Don't forget to subscribe, like, share, and comment below. Your engagement helps us build this community of hyperscale engineers and share these insights with the world. I'll see you in the next episode. Thank you for watching Catalyst Grid, building the machine at hyperscale. Stay safe and goodbye for now. This technical documentation is produced by DC Nordics. All technical specifications regarding FULCRUM campus cooling and WHR systems are strictly confidential and for internal professional review only. For further information on airside economisation, adiabatic cooling, or waste heat recovery agreements, please contact the lead scheduler's office. Building the machine at Hyperscale, Phase 1 complete. Thank you for your commitment to engineering excellence and sustainable infrastructure design. Catalyst Grid Series 2 will continue with Episode 11, technical documentation concluded.